Hello everyone. So today in this video we're gonna try to plot two-phase envelope for a compound on the PV isotherm we determined in the third video using the Maxwell construction. So on the right side we have our Maxwell construction, and Maxwell construction say that our lower area is equal to our upper area. And these three bounds for our areas are the V1, V1, V2, and V3 from the um, V1, V2, and V3 from the cubic roots of our cubic equation of state. So we're gonna try to use the root solver to find the values where our v's are equal to 0, but as uh, where our difference in integrals are equal to 0. So, let's just start by defining a function that will calculate us the integral of a function. So let's just define areas integral, right? It's gonna take p, t, and EOS SR. Okay, so we're gonna use this method. And our cubic equations of state has some variables of a, b, epsilon, and sigma, right? So we're gonna put it here, and we're gonna EOS here. So we already defined it for the function, and to calculate the integral, we're gonna use something called the nested integral. So we're gonna define integral. It's gonna take our v and return the integral. But before that, let's just calculate our integral. So let's go to Wolfram alpha. Let's just go to that. Okay, here we have our cubic equation of state. So integrate in no integral of p, like p minus, so we're gonna have everything inside of this. So, and it's gonna be in terms of v. And let's just start typing everything from in our cubic equation of state. So we're gonna have r multiplied by t over volume minus excluded volume minus a over so we're gonna have everything denominator here. It's gonna be volume plus epsilon times b, and volume plus sigma times b. And we're gonna have to close that. So if we check it, it is, so we need one more here and v here. So let's just integrate that. So let's just use our first calculated integral to in our functions, So let's just try to copy that. Okay, we're gonna have a bracket for numerator, bracket for denominator, and minus something and bracket. So it's gonna be RT NP log multiplied by NP log natural log. And as we know that our excluded volume is less than our actual volume, we're going to have to use the absolute value of this. So it's going to be b minus v, right? So let's just write everything in denominator. So it's going to be b times epsilon. Oh, I'm missing times. B times epsilon minus sigma, right? And for things in numerator, we're going to have a multiplied by nb log of b times s plus v minus 8 times uh, nb natural log of epsilon times b plus v, and plus, oh, it's b times pressure times epsilon plus sigma times volume, right? So this is our integral. So it's gonna, our function is gonna return that, and inside of our the original function for the integral, let's just, if we take a look at our Maxwell construction, so we have 3 bounds for our integral, right? So limits of integral. So it's going to be v1, v2, and v3 from our cubic roots of from cubic volumes of cubic equation of state. So we already have a function that will calculate us the cubic equation of state, right? So let's just get it and unpack it here. So we're gonna have v1, v2, v3 equals this one. And our function has to return the areas. So the first area, like this region, like the lower area, is the integral of v2 minus integral of v1. So we're gonna have integral of v2 minus integral of v1, right? And the second area, like the upper area, is integral of v3 minus integral of v2, second one, okay? So we're gonna have, so now we have our function for calculating the areas of Maxwell construction. So now let's have our another function that will calculate the difference between these two areas. So area, let's say diff, okay? So it's gonna have to take a vector. It's gonna have to take the temperature and EOS. It's gonna be SRK, like the methods, which method to use. And we're gonna give like the pressure, like vectors first thing. And it's gonna have to, okay, we know that this area is gonna be negative and this area is gonna be positive. So our, this function will get two outputs, which are the areas of these two, right? So let's just unpack them as left and right ones of area. So we're gonna have this function. Right here. Okay, and our function will return left plus right, because our left is negative. Okay, so it's gonna be our difference. Let's just run it, and then now we can try to plot this? Okay, we're gonna have a loop for several iterations in, and let's have some values that are linearly spaced, and like 0 with 7 difference until like 500. Okay, and let's just try to calculate vapor pressure, which is gonna be, we're gonna use the root solver. So SciPy integrate root solver. So it's gonna take like find a value where our areas, like different area difference, is gonna be equal to 0. So we're gonna have area difference. We need to provide our initial guess, but as we have our loop, we have to keep our initial guess changing. So let's just say, we'll just say it's a guess now for now. We're going to have our arguments, which are going to be our t-value and srk, the method. Okay, as it's going to be an array, like array for all the pressures, we will need only the x and the first element, like from x array. So we're going to isolate our x array and get the first value. Okay, so now here, let's just print, like give the value for temperature. Let's have it like from critical temperature minus 275 and multiplied by for our temperature, it's gonna have to be an exponential function so that we could plot this black line here. Okay, it's gonna be 1 minus np dot x of negative x, and we're gonna plus 275. Okay, and here, if we take a look at this, oh yeah, so our cubic function, like cubic v function, finds 3 v's, right? And we need now for plotting, we need only the v1 and the v3. And our v1, which is this point, is going to be our volume for liquid phase. And this point, which is v3, is going to be our volume for gas phase. So we don't need this point because it's actually not here. So we're going to have VL. As we don't need the second value, we're going to just define it as underscore, give it an underscore, and we're going to have let's have V gas, okay? And it's going to be cubic V, and it's going to have, this time it's going to get the values for value for pressure from vapor pressure, okay? And temperature. And let's have a list, as we need to plot this. Let's have a list for our 3 values. So let's have a list for our vapor pressure list, and let's make it empty list. And for our liquid volume list, and keep it empty. And gas volume, and we'll keep it empty. And inside of a loop, we are going to add the values in each iteration. So we're going to have P, like vapor pressure, list, append. And it's going to get the value from vapor pressure, calculated vapor pressure, and gonna add it to the list. And we're gonna have our liquid volume list dot append VL. So it's gonna take the volume, liquid volume, and gas volume. The same thing is gonna happen with this. So we're gonna append our values to the list in each iteration. And as we had our guess has to change so that our gas pressure is going to be like similar to the vapor pressure, because if the difference is too big, we're going to have an error message. So let's just define our, like, give our initial guess to be equal, let's say 100, okay? But for more accuracy, we're gonna say this guess is gonna be like, we'll update our value in each iteration to be equal to vapor pressure. So we'll be sure, like, we're gonna be sure that our guess is not far from the original answer, as it's gonna be like the value from the previous iteration. And outside of the loop, let's have like our pressure for plotting purposes. That's gonna be in our y-axis. Okay, it's gonna be P vapor list plus P vapor list the last element. And for our y-axis, like specific volume, we're gonna have V for plotting purposes, liquid volume list plus gas volume list the like the last element. Okay, so let's just run it. So we have error unsupported operand types for float and props. Okay. So the error was because we made a slight change, like we made a typo in this cubic V equation. So we forgot to include EOS, like the method. So the types were not like the same here, so that was causing an error. But now if we run this pvap, we're gonna have an error, like we're gonna have our uh, we're gonna have our array for the vapor pressure. Okay, let's just try to plot it now. Okay, if we try to plot it, we have to, let's have another like PV isotherm diagram. Let's just copy it, and we're gonna paste it. And it's gonna be our figure 2, figure 2, and figure 2. Let's make figure 2. Let's just plot it. So we have our second PV isotherm. And we're gonna have to plot. So it's gonna be figure 2, and it's not gonna be inside of a loop, because we cannot have like several loops, several lines for this. So we're gonna have figure 2 at, we're gonna have a scatter plot, and for our x we're gonna use our like volume for plotting purposes, and for our y we're gonna use our pressure for plotting purposes. And we're gonna have mode equal to, let's have lines, And for the, let's also define the line color. It's gonna be, let's have white. Like in a dark mode, it's gonna be visible. And if we plot it, oh, we're gonna have an error because we have to update our XPlot. Let's just try to give a range for our plot. Oh, here it shows an error here. And named user's color. Oh, it should be white. Sorry, yeah. Let's not include range. Oh, here it is. This is our PV isotherm for like two-phase plot, and let's just define a range for our X and have it like a greater range. And it's gonna be, let's have it as we're using like logarithms, let's have a range with the log from the minimum volume. So we're gonna have np minimum. This is the function. So we're gonna go from minimum volume. Let's go until -3. Oh, here is the problem. Yeah, it should be correct. Keyword argument. Yeah, we need this. Log np minimum p -3 range. Okay, let's not include range. Like here. So this is gonna be our two-phase envelope for our compound using the Maxwell construction. So this is our final graph. So thanks for your attention.